Deep in the cosmos, a black hole named LID-568 is breaking the rules of physics, devouring matter faster than theory says it should. How can something impossible be happening right now? Stay with us as we explore this cosmic enigma. If you enjoy mysteries like this, please like, subscribe and share, and tell us in the comments, do you think the universe still hides laws we haven't discovered? Thank you for watching. Now let's begin. In the deep silence of the early cosmos, the light that will one day reveal LID-568 begins its long journey. Space is dense with hydrogen and helium, the simplest elements formed in the first minutes after the birth of the universe. Gravity has begun its slow, inevitable work, drawing these atoms into clusters that will one day become galaxies. The cosmic microwave background still glows faintly, its radiation stretched thin across the expanding void, a memory of the first fire that once filled everything. The young universe is only a few 100 million years old, a fraction of its present age. Darkness dominates, yet within it lie the first small flickers of organized light. Proto-galaxies collapse within filaments of the cosmic web, their cores brightening as gas sinks inward and ignites the earliest stars. Among these ancient structures, one small region begins to outshine its neighbors. In that distant corner, the galaxy that will host LID-568 gathers itself from turbulent clouds. The young galaxy exists in a time of urgency. Matter moves more quickly, collisions between forming structures are more frequent, and the cosmic background is warmer. Heavy elements produced by the deaths of the first stars now seed the gas that flows inward, allowing new generations of stars to form more efficiently. Each supernova stirs the surrounding medium, compressing some clouds and dispersing others. The density of the environment feeds growth, but it also brings chaos. Radiation fields from nearby galaxies and the ultraviolet light of the reionization era strip electrons from atoms, creating regions of glowing plasma that thread through space. Within this energetic landscape, gravity continues its quiet persistence. The faint light of these events travels outward, spreading through the expanding universe, stretching with each billion years that passes. At this epoch, the cosmic web resembles a vast network of filaments and voids. The filaments act as highways along which matter flows toward nodes of higher density. These nodes are the young galaxies, connected yet isolated by the vastness of space. The gas streaming along these filaments is both the fuel of future stars and the raw material for supermassive black holes. Astronomers studying this distant age see not individual stars but the collective glow of enormous processes still in their infancy. The redshift of LID-568 marks it as belonging to this ancient time. Its light has travelled for billions of years, stretched by expansion, until only a fraction of its original energy remains. When telescopes capture it, they are not seeing the present, but the deep past, an image frozen in the moment when the first large black holes began to feed on their surroundings. The radiation detected from LID-568 is faint, but it carries distinct signatures. Emission lines reveal fast-moving gas and extraordinary luminosity far greater than what a typical young galaxy would produce. From such faint imprints, scientists infer a central engine of immense power. The surrounding stars contribute to the galaxy's brightness, but their combined output cannot explain the energy measured. Something within the core burns brighter than any stellar cluster, radiating with a steady persistence that defies easy explanation. Even at this early cosmic time, LID-568 behaves as if fully mature, its nucleus already active, consuming gas and dust at astonishing rates. The question arises of how such a massive object could have formed so quickly in a universe still in its early stages. The formation of supermassive black holes during this period remains one of the deep puzzles of modern astrophysics. Ordinary stellar black holes arise from the collapse of massive stars, but their growth to millions or billions of solar masses would require more time than the universe has yet allowed at this redshift. Some theories suggest that direct collapse from enormous gas clouds could create larger initial seeds, bypassing the slower path of stellar death and accumulation. Others consider dense star clusters that merge into a single heavy core. Yet the observational data of LID-568 stand apart even from these models. The intensity of its radiation and the scale of its apparent feeding suggest a mechanism that strains the limits of conventional growth. The environment of the early universe may have helped. Gas was more abundant and galaxies were smaller, meaning that gravitational interactions could funnel material inward more efficiently. Mergers between young galaxies would have destabilized their structures, pushing matter toward the centers. The higher density of the cosmic medium meant that every collision and compression delivered new supplies of fuel. In such a setting, an accreting black hole could grow rapidly, forming an accretion disk bright enough to be visible across the observable universe. Yet the luminosity implied by LID-568 still exceeds what should be possible even under these conditions. The light it emits rivals or surpasses that of entire galaxies, its energy output sustained rather than explosive. As the narrative of the early cosmos unfolds, the surrounding environment remains crucial. Beyond individual galaxies lies the intergalactic medium, a thin but pervasive sea of ionized gas filling the spaces between systems. This medium acts as both reservoir and barrier. It provides the raw material that galaxies draw upon, but it also absorbs and scatters light, shaping the faint signals that astronomers detect today. The glow of LID-568 must travel through this expanse, losing energy with each stretch of space it crosses. The photons that finally arrive carry the record of that journey, distorted, red-shifted yet unmistakably bright. Each one is a messenger from a time when matter condensed under conditions very different from those of the modern universe. The energy fields of the young cosmos interact continuously. Streams of radiation from the first quasars ionize nearby hydrogen, forming expanding bubbles of transparency that allow light to pass more freely. These bubbles gradually merge, clearing the fog of neutral gas that once filled space. It is within this emerging clarity that LID-568 shines. The epoch of reionization is ending, and galaxies like this one become visible through the thinning veil. Observations of such sources help define the timeline of the universe's awakening. Their light reveals not only the growth of structure, but also the temperature and composition of the intergalactic medium. To measure LID-568 is to trace the intersection of cosmic dawn and cosmic maturity, a moment when the first massive engines of energy begin to dominate their surroundings. At such vast distances, the human concept of time loses its ordinary meaning. The events described have already concluded billions of years ago, yet their light continues to arrive. The telescope's detectors convert these ancient photons into data, transforming what once was into what can now be seen. Every pixel recorded represents a tiny portion of history. The quiet hum of the instruments contrasts with the violence of the processes they reveal. LID-568's brilliance, reaching across space and time, offers a rare window into the extreme conditions of the early universe. Its behavior defies the comfortable boundaries of known physics, suggesting that even in these first epochs, the laws of radiation and gravity already competed in ways not yet fully understood. The scene remains one of stillness. On cosmic scales, motion slows to invisibility. Galaxies drift apart with expansion, their light fading imperceptibly. Within that calm, the faint flicker of LID-568 persists a beacon from a universe still young. Its photons continue their journey carrying the imprint of turbulent birth of energy, unleashed at scales beyond measure. They cross intergalactic space through dust and plasma, through epochs of change and cooling, until they reach the instruments that can finally translate their ancient story. The journey of light from LID-568 begins in chaos, and ends in observation connecting the infancy of the cosmos to the present moment of understanding. It is the first step inward, the outermost layer of a mystery that will unfold slowly one region at a time. The first faint detection of LID-568 comes as a flicker buried in survey data, a signal so distant that it appears almost at the threshold of perception. The photons reaching modern detectors began their journey billions of years ago, when the universe was still in its early youth. Each one has travelled through expanding space, its wavelength stretched by the cosmic scale factor, shifting from ultraviolet intensity to a faint infrared whisper. Astronomers use the term redshift to describe this stretching, a measure not only of distance but of age. The light from LID-568 carries a redshift so high that it represents an era when galaxies were newly formed, when hydrogen clouds still veiled much of the universe in opacity. Observing such an object is like looking backward through time, each increment of distance revealing a younger cosmos. Telescopes designed to study the early universe use wide-field surveys to scan the sky for sources like this one. At first, a LID-568 appears as a single dim blot on a deep image. Automated software flags it as unusually bright in certain wavelengths, indicating intense emission lines consistent with an active galactic nucleus. Follow-up observations with larger instruments confirm that the light is real and not an artifact. Spectroscopic analysis spreads the light into its component colours, revealing characteristic peaks, signatures of hydrogen, carbon, and oxygen, moving at extraordinary velocities. These lines are shifted far toward the red end of the spectrum, confirming the vast distance. The calculated redshift suggests that the light left its source more than 12 billion years ago. What the instruments now see is the echo of radiation emitted when the universe was less than 10% of its current age. Even at that distance, LID-568's brightness is remarkable. It stands out among galaxies of similar epoch, exceeding the luminosity expected from ordinary star formation. The spectral data indicate a compact source producing intense ultraviolet and X-ray emission, the hallmark of accretion, around a massive black hole. Yet the faintness of the signal also means that every photon matters. Researchers combine exposures taken over many nights, stacking the images to increase sensitivity, coaxing a clearer shape from the noise. Gradually a more defined profile appears. Around the central brightness lies a faint smudge of starlight, the host galaxy barely visible but present. Its light reveals something about the environment in which the black hole resides. The galaxy's colour and spectrum suggest ongoing star formation rich in dust and gas. In the early universe, such abundance is common, for cosmic matter has not yet been locked away in long-lived stars. The fuel supply is plentiful, and the conditions for feeding a central black hole are ideal. The data collected from LID-568 must then be calibrated against foreground interference. Light from intervening galaxies, cosmic dust and intergalactic hydrogen all alter the signal that finally reaches Earth. Astronomers use models of the intergalactic medium to correct for absorption and scattering. They identify narrow absorption lines caused by hydrogen clouds lying between the source and the observer. Each cloud at a different redshift leaves a mark on the spectrum, forming what is known as the Lyman alpha forest. By mapping these patterns, scientists can reconstruct part of the path that the light has taken through the cosmic web. The resulting corrected spectrum isolates the intrinsic features of LID-568 itself, allowing more accurate measurement of its luminosity and energy distribution. This process is slow and deliberate. Observatories on the ground and in orbit work together, collecting data across multiple wavelengths. Infrared telescopes capture the stretched radiation from the disk's outer regions. X-ray observatories measure the high-energy photons produced near the black hole's edge. Radio telescopes detect jets or outflows if present, extending far beyond the visible boundaries of the host galaxy. Each wavelength adds another layer of information, building a composite picture of a system too distant to resolve directly. The combined data form a portrait not of a single instant, but of a continuous emission that has persisted for millions of years. Such longevity implies a stable and powerful mechanism of energy production, far beyond the output of ordinary stellar processes. From this distance, LID-568's apparent brightness is deceptive. The inverse square law dictates that luminosity diminishes rapidly with distance. To appear as bright as it does at such redshift, the intrinsic energy output must be immense, on the order of trillions of times that of the Sun. The only known process capable of producing this sustained brilliance is accretion onto a supermassive black hole. Matter falling inward releases gravitational potential energy, converting it to heat and radiation with extraordinary efficiency. Yet even this explanation reaches its limit. The observed luminosity exceeds the theoretical maximum rate at which matter can be consumed without radiation pressure halting further inflow. That limit, known as the Eddington limit, defines the balance between gravity pulling matter inward and light pushing it outward. If the luminosity truly surpasses this boundary, by factors of 10 or more, it challenges the very framework that has guided astrophysical understanding for decades. The measurement of such excess requires careful validation. Astronomers test alternative interpretations. Could gravitational lensing by an intervening galaxy be magnifying the light? Detailed analysis of surrounding sources suggests not. There is no strong evidence of lensing features such as arcs or duplicate images. Could the emission come from a transient event such as a supernova or gamma-ray burst? The persistence of the signal over repeated observations rules this out as well. LID-568 maintains a stable brightness, varying only slightly over observed intervals. This steadiness indicates a continuous process, not a fleeting explosion. Each line of evidence reinforces the conclusion the galaxy hosts an active nucleus, radiating far beyond the limits set by classical theory. The detection of such a source has broader implications for cosmology. It adds to the growing population of early quasars that reveal massive black holes already in place less than 1 billion years after the Big Bang. Each discovery forces adjustments in models of black hole growth and galaxy evolution. The existence of LID-568 suggests that supermassive black holes can form rapidly and accrete matter at extreme rates, possibly aided by dense gas inflows and the compact structures of early galaxies. These observations reshape the understanding of how energy and matter interact at the dawn of cosmic history. To the instruments collecting its light, LID-568 is not an object but a pattern. It is a set of peaks, troughs, and gradients that together hint at a hidden architecture. Astronomers reconstruct its appearance through inference. They imagine the gas spiraling inward, the radiation pressure driving winds, and the magnetic fields threading through plasma. Yet all that reaches the detectors are photons that have travelled through billions of light-years of emptiness. Their arrival is a coincidence of time and survival, each one a survivor of countless interactions absorbed and re-emitted, deflected and redshifted, until finally captured by a sensor cooled to near absolute zero. The act of discovery is not a single moment, but a slow emergence from background noise, the universe revealing itself one photon at a time. Through this long observation, LID-568 becomes a reference point. It connects present-day physics with conditions that existed in the first chapters of cosmic evolution. Its light carries within it the history of expansion structure formation and the transformation of matter into energy. By studying it, scientists extend human perception backward in time, using instruments to bridge billions of years of silence. The detection of this galaxy is not merely an act of measurement, but a restoration of an ancient scene. It shows a universe already complex, already luminous, and already governed by processes that stretch the limits of known physics. The journey of discovery across deep time transforms a faint smudge of light into a window on how matter, gravity, and radiation began their intricate dialogue. Around the faint point of light that defines LID-568 lies a structure both elusive and intricate, a galaxy so distant that its details can only be reconstructed through inference. The host is barely resolved even in the deepest exposures, its shape discerned through subtle gradients of brightness that fade into the cosmic background. Observations from space-based telescopes reveal a diffuse halo of emission, extending outward from the nucleus, a sign that this galaxy is still young and actively forming stars. The light captured at near-infrared wavelengths shows uneven patches of intensity, evidence of clumpy regions where gas collapses under gravity. This irregular form contrasts with the smooth spirals and defined disks of later galaxies. In this early epoch, order has not yet emerged from the turbulence of creation. The host galaxy of LID-568 occupies a stage in cosmic history when star formation rates were dramatically higher than in the present-day universe. Within its boundaries, vast clouds of hydrogen condense and fragment into stellar nurseries. These regions glow in the ultraviolet as new stars ignite their radiation, ionizing the surrounding gas. The galaxy's overall color is therefore blue shifted toward the higher energies typical of young populations. Yet when this light finally reaches telescopes, it arrives red shifted to longer wavelengths, the memory of its original intensity preserved in stretched form. By comparing the brightness across filters, astronomers can estimate both the age of its stars and the dust content that obscures them. The data suggest a rich mixture of components, fresh bursts of star formation, interlaced with thick dust lanes that absorb and re-emit radiation in the infrared. This balance between starlight and dust defines much of the galaxy's visible structure. The dust arises from generations of earlier stars that lived short, violent lives enriching the interstellar medium with heavier elements. These particles scatter light, shaping the galaxy's appearance and regulating its temperature. In the case of LID-568, the dust not only absorbs ultraviolet radiation, but also re-radiates it as thermal emission. The glow detected in the far infrared bands indicates dense, warm regions possibly heated by both stars and the active nucleus. The result is a composite picture, a galaxy simultaneously bright and shrouded, its light escaping through irregular gaps in the surrounding haze. Such complexity hints at ongoing interaction between stellar evolution and the supermassive black hole that dominates the core. The morphology of LID-568 cannot be described by classical categories like spiral or elliptical. Its form is chaotic, asymmetric, and clumpy, consistent with galaxies observed at similar redshifts. The irregular structure likely results from repeated mergers and the inflow of cold gas from cosmic filaments. These processes drive turbulence, compressing clouds in some regions while dispersing them in others. Computer simulations suggest that in this period of cosmic time, galaxies grow rapidly through such collisions, each event stirring the central potential well and sending waves of gas toward the nucleus. The host of LID-568 may therefore be in the midst of assembly, its outer regions merging while its core already blazes with quasar-like intensity. To map such a galaxy requires combining data from multiple instruments. Optical images show the extended starlight, but infrared observations penetrate deeper into the dusty core. Millimeter arrays detect emission from carbon monoxide and other molecules tracing the cold gas that fuels star formation. These molecular lines act as markers of density and motion. By measuring their Doppler shifts, astronomers can estimate how gas circulates within the galaxy, how fast it rotates, and how much mass it contains. For LID-568, the results indicate rapid internal motion, suggesting a gravitationally bound system dominated by a central mass far larger than the combined mass of its stars. The inference is that a supermassive black hole already mature anchors the center. The distribution of gas and dust tells another part of the story. Maps constructed from sub-millimeter observations reveal concentrations near the nucleus, forming dense reservoirs that could feed the accretion disk. These clouds likely flow inward along unstable gravitational channels created by the galaxy's irregular potential. Outside, the core extended filaments stretch toward the edges, faint traces of material being drawn in from the cosmic web. The morphology implies both inflow and feedback. While some gas moves inward to sustain the central engine, other portions may be expelled by powerful winds generated near the accretion region. This dynamic interplay between feeding and outflow shapes the entire structure, determining the rate of growth and the future evolution of the galaxy. In the broader context of its surroundings, LID-568 appears not as an isolated system, but as a node within a small proto-cluster of galaxies. Deep-field imaging reveals neighboring sources with similar redshifts hinting at early-stage clustering. Such proximity would enhance interactions leading to tidal disturbances that channel additional matter into the central region. The environment itself may therefore be complicit in fueling the black hole's rapid growth. Each nearby galaxy contributes gravitational torques that destabilize the system, compressing gas and driving it toward the nucleus. The result is a feedback loop. The more matter falls inward, the more energy is released, and the more the surrounding structure is reshaped by radiation and motion. Astronomers analyzing LID-568 focus on its spectral energy distribution, a measurement of brightness across wavelengths. The curve of this distribution reveals multiple components. A steep rise in the infrared marks warm dust heated by intense radiation. A plateau in the optical range corresponds to starlight from young populations. Beyond that, in the X-ray domain, a sharp increase indicates high-energy processes near the black hole. Together, these features confirm that the host galaxy and its nucleus are deeply intertwined. The galaxy provides the fuel, and the black hole returns energy to its surroundings, heating, ionizing, and sometimes expelling material. This exchange regulates both growth and destruction, a balance that determines how long the galaxy can maintain such extreme luminosity. The challenge of studying such a remote object lies not only in its distance, but in the interpretation of its limited light. Every pixel of data represents billions of stars compressed into a single measurement. The noise of detectors and the fluctuations of cosmic background radiation blur details that would otherwise reveal structure. Yet through repeated observation and careful modeling, scientists reconstruct a plausible image. They envision a compact irregular galaxy, its inner regions blazing with radiation, its outskirts still forming stars. Around it, faint halos of ionized gas extend outward, perhaps illuminated by the central quasar. The entire system is caught in a moment of transformation, evolving faster than any modern analogue. In comparing LID-568 with other high redshift galaxies, astronomers note both similarities and extremes. Many young galaxies at this epoch exhibit rapid star formation and active nuclei, but few display the same degree of luminosity and compactness. The galaxy's spectral features suggest metallicity is higher than expected for its age, implying rapid chemical enrichment. This means that earlier generations of massive stars must have lived and died quickly, seeding the interstellar medium with heavier elements that now cool the gas and facilitate further collapse. Such accelerated evolution may explain how the black hole at the center could grow so massive so soon. The host galaxy thus becomes both an accomplice and a witness to the violation of normal physical limits occurring within it. Viewed through time, LID-568 is not a stable form but a transient configuration, a snapshot of growth under conditions of extreme density and radiation. Its shape, brightness, and composition will change as billions of years pass, though the transformation will never be observed directly. The photons recorded today capture only a single interval in an unending process of collapse heating and dispersal. To map this galaxy is to freeze motion to extract order from a chaos that still continues elsewhere in space-time. What the instruments describe is a brief illumination within a long cosmic sequence, a structure both incomplete and yet already bound to the laws that will govern galaxies thereafter. In the faint outline of its host, the story of LID-568 gains its first tangible frame, a vessel of dust, gas, and stars surrounding an unseen force that consumes matter faster than physics allows. Within the galaxy that hosts LID-568, space is far from empty. Clouds of gas and dust drift through its structure, colliding, merging, and collapsing under the relentless pull of gravity. This interstellar medium forms the raw substance of stars and the eventual nourishment of the central black hole. At these early cosmic times, the density of gas is immense, far higher than in galaxies of the present era. Molecular hydrogen dominates, interwoven with trace amounts of heavier elements like carbon, oxygen, and silicon. The radiation from young stars ionizes pockets of this medium, creating glowing nebulae that flicker amid the darkness. Cold regions shielded by dust provide the birthplace of future stellar generations. Every particle, every atom participates in a slow circulation that extends from the outskirts of the galaxy to its blazing core. The behavior of this interstellar matter is governed by turbulence. Shockwaves from supernovae and stellar winds generate chaotic motion that mixes the gas and redistributes energy. Observations of spectral line broadening in LID-568 reveal velocities reaching hundreds of kilometers per second, an indication that this turbulence pervades the entire system. Some regions collapse as pressure drops, forming dense knots where stars ignite. Others expand as heat and radiation drive them outward. The result is a dynamic equilibrium, a constant exchange between creation and dispersal. In this restless environment, nothing remains still. Gas clouds spiral toward the nucleus along gravitational channels carved by the uneven distribution of mass. Each orbit brings them closer to the point where rotation and infall balance in a delicate dance. The interstellar medium serves as the link between the galaxy's outer regions and its central engine. Material stripped from the outskirts through tidal forces or minor mergers flows inward through lanes of higher density. These filaments act as cosmic rivers guiding the gas toward the center. The molecular component of the gas, traced through carbon monoxide emission, reveals elongated structures connecting distant parts of the galaxy to its nucleus. Within these conduits, gravity compresses the material, while collisions dissipate angular momentum, allowing the inflow to proceed. The rate of transport is extraordinary, suggesting that vast quantities of matter reach the inner few hundred parsecs in comparatively short cosmic timescales. As the gas approaches the core, radiation from the active nucleus begins to influence its state. Ultraviolet photons ionize the outer layers of clouds, heating them to thousands of degrees. X-rays penetrate even deeper, breaking molecular bonds and generating a plasma of charged particles. These processes create complex zones of ionization, where cold molecular gas coexist with hot, highly energetic regions. Observations show that such multiphase structures are typical of galaxies hosting luminous quasars. In LID-568, the balance between heating and cooling defines how efficiently the inflow continues. If radiation pressure becomes too strong, it can halt or even reverse the inward movement. Yet evidence suggests that despite intense luminosity, the galaxy maintains a steady supply of fuel, implying a geometry or mechanism that shields portions of the inflow from direct radiation. Dust plays a subtle but critical role in this process. Each tiny grain acts as a mediator between light and matter. Dust absorbs high-energy photons and re-emits them as longer wavelength infrared radiation, allowing energy to escape without completely halting the collapse of gas. The presence of dust also aids the formation of molecular hydrogen by providing surfaces where atoms can combine. In LID-568, the infrared brightness indicates a large dust mass possibly concentrated in toroidal structures around the nucleus. These dusty regions regulate the temperature and pressure of the surrounding medium, permitting the continuous inflow of material despite the intense radiation field near the black hole. Without dust, the feedback from the central source would likely disperse the gas before it could reach the accretion disk. Interstellar magnetic fields further shape the motion of matter. Although invisible, their influence becomes evident through polarization measurements and the alignment of dust grains. Magnetic tension resists compression in certain directions, guiding gas along field lines and stabilizing large clouds against collapse. Yet as material falls inward, magnetic energy can also be twisted and amplified, converting kinetic motion into electromagnetic stress. In regions where turbulence stretches these lines, reconnection events may release bursts of heat and radiation. Such magnetic processes contribute to the overall dynamics of the galaxy, redistributing angular momentum and perhaps aiding the final stages of accretion. In LID-568, the exact configuration of magnetic fields remains uncertain, but their indirect signatures suggest a complex interplay between gravity radiation and magnetism. From a macroscopic view, the galaxy functions as a vast recycling system. Stars form from gas shine for millions of years, and then return enriched material to the interstellar medium through winds and supernovae. This enrichment increases the metallicity of subsequent generations, improving the efficiency of cooling and promoting further star formation. At the same time, part of the gas never joins stars but continues to drift inward, ultimately captured by the central gravitational well. Thus, stellar evolution and black hole growth are not separate processes, but intertwined phases of a single galactic metabolism. The brightness of LID-568 reflects this continuous flow of energy from gravitational potential to light, from matter to radiation. The movement of interstellar matter also affects the shape and stability of the galaxy. Regions of intense star formation generate pressure that can push against the infalling gas, producing outflows that counteract the inward pull of gravity. These outflows carve cavities and channels through which radiation escapes. In high-resolution simulations, similar feedback patterns create ring-like or clumpy structures around active galactic nuclei. If LID-568 behaves in this manner, its central region may be surrounded by shells of expanding gas, each marking an episode of intense energy release. Over time, such cycles could regulate the rate at which new material reaches the core, maintaining a quasi-steady state despite extreme conditions. When viewed through the instruments that capture its faint light, the interstellar medium of LID-568 is reduced to patterns in a spectrum: broad lines, shifted peaks, subtle asymmetries. These features encode velocity, temperature, and density, translating vast processes into measurable data. From these patterns, scientists reconstruct the invisible flows that sustain the galaxy's luminosity. They imagine streams of gas winding through dusty corridors, clouds colliding and merging filaments stretching from the outer halo to the nucleus. Each element of this imagined scene corresponds to physical reality, though none can be seen directly. The interpretation emerges not from imagery, but from the language of light itself, measured photon by photon across long nights of observation. The steady inward migration of matter ensures that the nucleus never starves. As long as the galaxy's reservoirs remain abundant, the black hole at its center can continue to feed at extraordinary rates. Yet this process carries within it a paradox. The same inflow that sustains the brightness of LID-568 also builds the conditions for its eventual decline. As gas is consumed or expelled, the fuel supply diminishes and the galaxy's radiance will fade. In this distant epoch, however, the system still thrives in its prime. Interstellar matter flows through its structure like blood through a living organism's circulating energy, forming stars and nourishing the gravitational heart that devours everything drawn too close. Within this movement lies the quiet power that defines the galaxy, a continuous, slow-burning transformation of matter into light, a motion that binds creation and destruction within the same cosmic rhythm. At the heart of LID-568 lies a region where the force of gravity overcomes every other influence. It is a space where light bends, time slows, and matter loses its individuality to a deeper order. The stars near this core orbit at extraordinary speeds, their motion betraying the presence of a massive yet invisible object. From their velocities inferred through spectral shifts, astronomers deduce a mass millions or perhaps billions of times that of the Sun, compressed within a volume smaller than the solar system. This concentration of mass forms what physics defines as a supermassive black hole, an entity whose gravity is so intense that not even radiation can escape once it crosses the critical boundary known as the event horizon. Yet paradoxically, it is this same object that powers the galaxy's luminous center. The gravitational potential well created by this mass governs the behavior of everything around it. Stars' gas clouds and even dust grains respond to its pull, moving in complex orbits that gradually decay through friction and collisions. The closer matter approaches, the faster it must move to remain in orbit, until velocity reaches a limit where rotation alone can no longer resist collapse. This process transforms ordered motion into heat, and heat into radiation. In the vicinity of LID-568's core, gravity acts not only as a sink, but as an engine converting the energy of infall into the light that makes the system visible across the universe. The result is an apparent contradiction, a source of immense brightness generated by something that itself emits nothing. The evidence for such a black hole arises from more than theory. Observations of similar active galaxies show that their central masses correlate with the properties of their hosts: the velocity dispersion of stars, the bulge mass, the luminosity of the nucleus. These relationships, established across cosmic distances, suggest a deep coupling between black hole growth and galactic evolution. In LID-568, the balance is extreme. The black hole's inferred mass is disproportionate to the young galaxy surrounding it, indicating rapid formation before the host itself matured. This inversion challenges standard models that place black hole development as a gradual consequence of galactic assembly. Here the center appears to have outpaced its environment, forming a gravitational anchor that shapes everything else. The gravitational field around such an object can be described in terms of space-time curvature. Near the core, geometry itself is distorted, and the paths of photons bend into arcs that wrap around the invisible mass. The event horizon marks the threshold beyond which all trajectories lead inward, an ultimate surface separating the knowable from the unknowable. Outside this limit, matter can still orbit, forming rings of plasma that radiate intensely as they spiral closer. This region, known as the accretion zone, becomes the visible manifestation of the black hole's presence. Though the hole itself cannot be seen, the energy released by infalling material illuminates its surroundings. In the case of LID-568, that illumination reaches levels far exceeding theoretical expectations. Within the gravitational well, forces vary across scales. At greater distances, stars follow near Keplerian paths, their motion predictable through Newtonian dynamics. Closer in, relativistic effects dominate. Time dilation, frame dragging, and gravitational redshift alter the behavior of matter and radiation. For the gas approaching the inner edge of the accretion disk, these relativistic phenomena define how energy is released and how the disk maintains its structure. Photons climbing out of this deep potential lose part of their energy, their wavelength stretched by gravity itself. To distant observers, this red-shifted radiation forms part of the characteristic spectrum that identifies active galactic nuclei. The signatures observed in LID-568 confirm that its light originates from a region where gravity operates near its most extreme form, short of a black hole merger. The scale of this gravitational well has profound effects on the surrounding galaxy. The intense acceleration near the center stirs turbulence throughout the inner regions, disrupting stellar orbits and redistributing gas. This agitation can both trigger and suppress star formation depending on local conditions. In dense pockets shielded from radiation compression by tidal forces, can induce collapse and produce new stars. In exposed areas, the same tidal effects tear clouds apart before they can condense. Thus, the gravitational field functions as both a creative and a destructive agent. Over cosmic time, it sculpts the inner morphology of the galaxy, determining where stars can survive and where matter must yield to the central pull. At the outer edges of this domain, the gravitational influence merges with the overall potential of the galaxy. Here, dark matter also contributes, forming a diffuse halo that stabilizes the system against disruption. Though invisible, dark matter provides the framework upon which baryonic material, ordinary matter made of atoms, collects and moves. Without this hidden scaffolding, the immense gravitational energy of the nucleus might have torn the galaxy apart. Instead, the interaction between visible and invisible mass maintains equilibrium, allowing LID-568 to exist as a coherent structure rather than as a chaotic scatter of fragments. In this balance between attraction and containment, the galaxy sustains its brightness and its form. Within the gravitational well, magnetic fields thread through ionized plasma twisting as they follow the curvature of space. These fields can store enormous amounts of energy, occasionally releasing it in bursts that accelerate particles to relativistic speeds. In many active galaxies, such processes generate narrow jets that extend thousands of light-years into space. Although direct evidence of jets in LID-568 remains uncertain due to distance and faintness, The presence of synchrotron emission hints that magnetic activity plays a role. Such energy transport mechanisms may help regulate the inflow of matter by carrying angular momentum away from the disk, allowing continued accretion despite the outward pressure of radiation. From a thermodynamic perspective, the gravitational well operates as a vast converter. Potential energy lost by falling material reappears as radiation heating and mechanical motion. The efficiency of this process can surpass that of nuclear fusion making black hole, accretion the most potent known mechanism for energy release in the universe. Even a small fraction of mass consumed produces enormous luminosity. For LID-568, this conversion seems to occur at rates that violate the classical limit of stability. Yet from the standpoint of observation, the evidence is clear. Light emerges from the region surrounding the black hole at intensities tens of times higher than models allow. Gravity, it seems, does not merely confine, it enables a form of cosmic overproduction where the constraints of equilibrium are temporarily suspended. The concept of a gravitational well invites a simple image, yet its reality defies intuition. In the curved space-time near the core, distances and durations lose familiar meaning. A particle falling inward experiences only moments before reaching the horizon, while to a distant observer the same fall appears to take eternity. Energy released in that descent radiates outward, carrying the mark of time slowed by gravity. In every photon emitted from LID-568's nucleus lies this compression of history, a record of motion slowed, energy transformed, and matter dissolved into the geometry of space itself. As observations accumulate, the gravitational well at LID-568 remains a reference point for understanding how the universe's most extreme engines operate. It demonstrates how structure arises from collapse, how energy emerges from confinement, and how the deepest pull of gravity can paradoxically create the brightest beacons of light. Within this region, the laws of motion and thermodynamics converge at their limits. The invisible mass at the center of LID-568 is not only the cause of its brightness, but the framework through which the surrounding galaxy sustains itself. The gravitational well defines the galaxy's identity, binding every atom, photon, and star to the quiet tyranny of a single immense force that consumes all paths leading inward. The great gravitational well at the heart of LID-568 does not feed by chance. It depends on vast networks of structure that stretch outward through the galaxy, subtle but persistent conduits through which matter drifts toward annihilation. These feeding channels are invisible in ordinary light, yet revealed through the motions of gas traced by emission lines. Across thousands of light years, patterns emerge: streams, filaments, and elongated arms that transport material from the outskirts into the central few hundred parsecs. The motion is slow on human scales, yet relentless on cosmic ones. It is driven by gravity, aided by instability, and guided by the asymmetry of the galaxy itself. Over millions of years, this quiet transport sustains the brightness that defines LID-568's identity. Within many galaxies, large-scale structures such as bars and spiral arms serve as engines of angular momentum transfer. In LID-568, whose shape is irregular and still forming, these mechanisms manifest as dense, lopsided regions rather than graceful spirals. The uneven distribution of mass creates tidal torques that act like gears pushing gas inward. Simulations of early galaxies suggest that such torques can funnel vast quantities of material toward their centers in surprisingly short timescales. Observations of molecular lines in LID-568 confirm this idea. Cold gas clouds are moving at velocities of several hundred kilometers per second toward the core, compressed and heated as they descend. In this environment, Gravity does not pull uniformly. It channels, focuses, and bends trajectories until all paths converge at the nucleus. The process of inward transport requires the loss of angular momentum. Gas orbiting the galactic center cannot simply fall straight inward. It must shed its rotational energy through collision shocks or magnetic coupling. Within LID-568 regions of dense gas collide with one another, converting orbital motion into heat and radiation. Dust grains within these regions act as lubricants, absorbing energy and cooling the gas enough to continue its inward journey. Over time, this leads to the formation of coherent inflow streams that spiral toward the central 100 parsecs. Each collision, each compression brings matter one step closer to the gravity that will consume it. The scale of the inflow is enormous, involving masses equivalent to thousands of suns each year. For comparison, the Milky Way today feeds its own nucleus at rates millions of times smaller. LID-568 therefore represents an extreme, a galaxy caught in the act of rapid self-fueling. The morphology of the inflow region shows a mixture of order and turbulence. Along some paths, the gas forms continuous filaments that remain stable over long distances. Along others, it fragments into clumps torn apart by tidal forces. Magnetic fields thread through these flows, guiding ionized matter along invisible lines of tension. These fields can channel plasma efficiently, while also generating resistance against collapse, controlling how quickly material reaches the central reservoir. In certain zones, the fields twist into spirals that resemble the larger structure of the galaxy itself, mirroring the hierarchy of motion from kiloparsec scales down to subparsec scales. Though the exact geometry remains unresolved, polarization measurements suggest that magnetic organization plays a critical role in maintaining coherence amid chaos. As gas approaches the circumnuclear region, gravitational compression heats it to tens of millions of degrees. The radiation emitted from this hot plasma contributes to the galaxy's X-ray luminosity. Yet much of the matter remains shielded within dense, dusty flows, invisible to optical light, but brilliant in the infrared. These warm streams continue to lose angular momentum through viscous interactions until they merge with the forming accretion disk. Their rotation becomes dominant again, and the inflow transforms into circular motion around the event horizon. The feeding process thus spans a continuum from large, slow galactic inflows to the rapid relativistic dynamics of the inner disk. Each stage feeds the next, forming a chain of motion that connects the outer galaxy to the black hole itself. Not all of the matter drawn inward reaches the center. Portions are diverted or expelled by radiation and winds from the nucleus. These feedback processes sculpt the surrounding region into a complex landscape of inflow and outflow, with turbulent boundaries where energy is exchanged. The balance between these opposing motions determines how long the system can remain active. If inflow dominates, the black hole grows and brightens. If feedback wins, the supply is cut off and the galaxy dims. In LID-568, the persistence of extreme luminosity implies that inflow continues to outpace outflow, at least for now. The gravitational appetite of the central engine remains well fed. The efficiency of these feeding channels depends heavily on the geometry of the host galaxy. In more ordered systems, such as mature spirals, stable rotation can hinder inflow by conserving angular momentum. In contrast, LID-568's irregular structure and high gas fraction make it unstable and ideal environment for rapid inward transport. Turbulence replaces order and asymmetry becomes an advantage. The same instabilities that might disrupt a modern galaxy instead drive the flow here, compressing and funneling matter with violent efficiency. Observations of high redshift systems show similar behavior, suggesting that this mode of feeding was common in the early universe, when gas was abundant and galaxies were still assembling. On smaller scales, gravitational resonances amplify the effect. As clouds orbit near the nucleus, their paths intersect at predictable locations, where density waves concentrate matter. These resonances act like conveyor belts, repeatedly guiding gas toward the same regions. Collisions at these points trigger bursts of star formation, which in turn inject energy and momentum into the gas, further altering its path. This cyclical exchange creates a rhythm within the galaxy: inflow, compression, starburst feedback, and renewed inflow. In LID-568, the rhythm accelerates, operating at frequencies far beyond those observed in calmer systems. The result is a continuous surge of material spiraling inward, a self-sustaining flow that fuels both stellar birth and black hole growth. The presence of such organized inflows across multiple scales reveals how galaxies evolve in cooperation with their cores. LID-568 is not a passive structure surrounding an isolated black hole. It is an integrated machine in which every part contributes to a single outcome: the transport of matter toward the deepest gravitational potential. The gas clouds in the outskirts, the turbulent filaments in the middle regions, and the hot plasma near the nucleus all form parts of one grand mechanism. Over millions of years, this mechanism transforms the gravitational energy of the entire galaxy into radiation, emitted from a point smaller than a solar system. As observers analyze the light from LID-568, they are effectively tracing the map of these hidden pathways. Each spectral line encodes information about velocity, temperature, and density along a different segment of the inflow. Together they reveal a system in perpetual motion, one that challenges the very idea of equilibrium. Gravity and radiation compete for dominance, yet neither wins completely. The result is a steady but unstable balance, a galaxy devouring itself while sustaining its own radiance. In this ongoing process, time loses clarity. The feeding channels evolve over millions of years, yet their product, the light that now reaches Earth, seems instantaneous. Each photon carries the sum of countless interactions, collisions between clouds, the shearing of gas, flows, the heating of dust, the pull of gravity. To observe LID-568 is to witness the end of that long journey, to see the culmination of movement that began when the universe was still young. Inward motion defines the life of this galaxy. Every particle drawn toward the center contributes to the same fate, falling into the gravity well that bends space and time until energy itself becomes light. The feeding channels of LID-568 are the unseen arteries of a cosmic organism, forever circulating matter toward the dark heart that sustains its brilliance. As matter drawn through the feeding channels approaches the central few light-years of LID-568, its movement transforms from chaotic drift into organized rotation. The inward motion slows, stabilizing into an orbit around the massive core. Friction between adjacent layers of gas converts motion into heat, and the once invisible streams of hydrogen and dust ignite into a disk of radiant plasma. This structure, known as the accretion disk, becomes the brightest feature of the galaxy, a thin, spinning sheet that encircles the black hole and releases energy at a scale beyond any other known process in the universe. Here matter changes form, gravitational energy becomes heat, and heat becomes light. In this small region, smaller than the solar system yet brighter than the combined light of billions of stars, the identity of LID-568 as a quasar fully emerges. The physics of the accretion disk depend on balance and friction. Every particle within the disk moves at near relativistic speeds, orbiting in precise layers where velocity increases toward the center. Collisions between particles generate viscosity, which transfers angular momentum outward and allows mass to move inward. The outer regions remain relatively cool, glowing faintly in the visible and ultraviolet. Closer to the core, temperatures rise to millions of degrees, causing the gas to radiate in X-rays. The gradient from cool to hot defines the disk's structure and spectrum. Observations of LID-568 reveal this temperature distribution clearly, its emission rising steeply at shorter wavelengths, consistent with a dense, rapidly spinning disk. The light varies subtly over time, flickering as instabilities ripple through the plasma. These variations act like fingerprints, confirming the dynamic nature of the process. The formation of such a disk begins with angular momentum conservation. Gas falling toward the black hole cannot collapse directly, it must orbit. Over time, collisions flatten the flow into a thin plane, aligned with the equator of rotation. The inner edge of this disk lies at the innermost stable circular orbit, a radius defined by general relativity, where gravity is strong enough that any closer path would plunge directly into the event horizon. At this boundary, matter accelerates to a significant fraction of the speed of light. The energy released in this motion is vast, rivaling the total energy output of all stars in the host galaxy. The efficiency of this conversion, reaching nearly 10% of the rest mass energy, makes accretion the most effective known power source in the cosmos. Around LID-568, the evidence for this disk is indirect but unmistakable. The spectrum shows the classic shape of multi-temperature blackbody emission, with specific lines broadened by extreme rotation. The pattern of light polarization indicates that the radiation is not emitted isotropically, but arises from a flattened rotating structure. Furthermore, high-energy X-ray observations detect a feature known as the iron K-alpha line, distorted into a skewed profile by the effects of relativistic motion and gravitational redshift. This distinctive curve confirms that the emission originates from gas orbiting deep within the gravitational field of the black hole. Each photon carries information about velocity curvature and distance from the event horizon, allowing astronomers to infer the disk's geometry even from billions of light-years away. The disk is not a static object, but a turbulent sea of plasma threaded by magnetic fields. These fields arise naturally from the motion of charged particles, and they interact with the flow in complex ways. Twisting lines of magnetism generate shear amplifying turbulence and enhancing the transport of angular momentum. In certain conditions, magnetic tension can lift material from the disk's surface, launching it outward as a wind or jet. Although direct imaging of such features in LID-568 remains impossible, the observed variability in its light suggests that similar processes occur here. The magnetic fields also contribute to the overall stability of the disk, preventing fragmentation while maintaining a steady inflow toward the black hole. Without these invisible forces, the disk might collapse or disperse under its own energy. As energy is released, radiation pressure builds within the disk. This pressure acts against gravity, pushing material outward and setting an upper limit on how fast the black hole can consume matter. This theoretical threshold is the Eddington limit, and under normal circumstances accretion stabilizes near it. However, in LID-568, the observed luminosity exceeds this boundary by an order of magnitude or more. The implication is that the disk operates under super-Eddington conditions where radiation escapes not uniformly, but through narrow channels or funnels in the plasma. In such regimes, part of the emitted light is trapped and carried inward by the inflowing matter, effectively allowing the black hole to consume material faster than radiation pressure would otherwise permit. The disk becomes thick and distorted, resembling a luminous torus rather than a thin sheet. Within this geometry, outflows may coexist with inflows, with photons escaping preferentially along the poles, while gas continues to spiral inward through the denser equatorial plane. The accretion disk also defines the appearance of the galaxy's nucleus. To an observer, its orientation determines brightness and spectrum. When viewed face-on, the light escapes more directly, revealing the ultraviolet and X-ray intensity of the inner regions. When seen at an angle, dust and gas obscure part of the emission, and the galaxy appears redder, dominated by infrared re-radiation from heated material. The diversity of observed quasars across the universe may arise largely from such orientation effects. In the case of LID-568, the consistency of its brightness suggests a relatively unobstructed view, implying that the disk is tilted, so its radiating surface is partly visible from our line of sight. Through this fortunate alignment, the full extent of its extraordinary luminosity can reach distant detectors. Inside the disk, matter follows a one-way path toward the horizon. As it spirals inward, it encounters increasing friction and heat until atoms themselves break apart into plasma. Electrons and protons move independently, producing synchrotron radiation as they spiral along magnetic lines. The energy released in this zone dominates the galaxy's emission, a continuous flood of light that masks the faint starlight around it. Yet even as the disk radiates, it also evolves. The inner regions may thicken with time as energy builds, while outer regions may fragment under gravitational instability, forming transient clumps that migrate inward. These fluctuations cause the subtle changes in brightness recorded over months or years, the flicker of a cosmic engine operating near the limits of physics. The creation of the accretion disk marks the transition from hidden gravity to visible power. It is the interface where matter's fall becomes light's release, where destruction turns into radiance. The balance of forces within it, gravity pulling inward, radiation pushing outward, magnetism twisting through plasma, defines the stability of the entire system. The observations of LID-568 show that this balance is being maintained far beyond the levels once thought possible, suggesting mechanisms of feedback and self-regulation that are not yet fully understood. For now, the disk continues to burn, converting the galaxy's infalling gas into a torrent of energy that travels across cosmic time. In that steady rotation, in that continuous transformation, the accretion disk becomes the true heart of LID-568, the structure through which the universe's most powerful gravitational engine makes itself known through light. At the center of astrophysical theory lies a delicate boundary that separates stability from runaway growth. This boundary is known as the Eddington limit, a threshold that defines the maximum luminosity a body powered by accretion can sustain before its own radiation pushes away the matter that feeds it. It is the invisible line where gravity's pull inward is exactly balanced by the outward pressure of light. To exceed this limit is in principle to break the symmetry that allows a system to endure. In ordinary circumstances, a black hole that accretes beyond this rate would expel its fuel through radiation pressure, halting further feeding. Yet LID-568's behavior suggests that nature sometimes finds a way to operate beyond this apparent ceiling. To understand why its brightness defies expectation, one must first understand the simple logic of the limit itself. In its essence, the Eddington limit describes the equilibrium between two forces acting on the infalling gas. The first is gravity pulling matter toward the massive object. The second is radiation emitted by the hot plasma as it releases gravitational energy. Each photon of light carries momentum, and when that photon encounters an atom or an electron, it transfers part of that momentum outward. The result is a counterforce, a pressure generated by light itself. When the rate of radiation becomes high enough, this pressure equals the gravitational pull acting on the gas, and a balance is achieved. If radiation increases further, the gas can no longer move inward. It is pushed outward instead. The luminosity corresponding to this state of balance is the Eddington luminosity. It depends only on the mass of the central object and the opacity of the surrounding material. For a given black hole, it represents the theoretical maximum sustainable brightness without expelling its own fuel. This limit serves as a cornerstone of astrophysics, applying not only to black holes, but to stars, neutron stars, and any object powered by radiation from infalling matter. In practice, it establishes a relationship between mass and light. The more massive the object, the higher the luminosity it can sustain before reaching equilibrium. For a black hole of several billion solar masses, the Eddington luminosity corresponds to an energy output roughly 10 trillion times that of the Sun. It is a vast but finite figure derived from the same physical constants that govern all light-matter interactions. Most observed quasars and active galactic nuclei radiate near or below this value, their behavior consistent with the theoretical boundary. LID-568, however, shines with power far beyond it, by factors of 10, 20, or even 30. The discovery of such excess prompts re-examination of the assumptions behind the limit. The classical formulation presumes spherical symmetry and steady flow. In reality, accretion disks are neither. Their geometry is flattened, their density uneven, and their radiation anisotropic. Light escapes more easily along the poles than along the plane of the disk, creating channels through which energy can leave without directly opposing the inflow of matter. In these circumstances, a system can exceed the nominal Eddington limit without violating the underlying physics. The radiation pushes outward only in certain directions, while gas continues to fall inward through others. This configuration, sometimes called super-Eddington accretion, may describe what occurs in LID-568. The light emitted appears to surpass the limit, but much of it is channeled away from the paths followed by the infalling material, allowing accretion to proceed. Even with this explanation, the numbers remain extraordinary. Observations of LID-568's X-ray and ultraviolet luminosities imply accretion rates tens of times the canonical Eddington value. The energy output corresponds to a black hole consuming several solar masses of gas each year, converting a fraction of that mass into radiation with near-perfect efficiency. To maintain such a regime, the system must possess powerful feedback mechanisms that prevent complete disruption. Theoretical models suggest that thick radiation-dominated disks can achieve this balance. Within them, photons are trapped by scattering and carried inward with the flow, reducing the net outward pressure. The result is a kind of self-shielding structure in which radiation and matter coexist in an uneasy but stable coexistence. LID-568's light may therefore represent the visible surface of a far deeper and more complex engine, operating at the boundaries of known stability. The Eddington limit also defines how fast a black hole can grow. Because luminosity limits accretion, the rate of mass increase is constrained by the same physics. For a system radiating at the Eddington rate, the timescale for its mass to double, the so-called salpeter time, is about 40 million years. Growth faster than this would normally be prevented by radiation feedback. Yet LID-568's super-Eddington behavior implies that its black hole may have grown far more rapidly than expected, reaching billions of solar masses in less than a billion years after the Big Bang. Such efficiency helps explain how massive quasars already existed in the early universe, but it also raises questions about what conditions permitted such sustained violation of the classical limit. Measurements of LID-568's spectrum reveal signatures consistent with this scenario. The broad emission lines indicate dense high-velocity gas near the nucleus, while the relative weakness of narrow lines suggests that much of the radiation escapes in confined directions rather than illuminating the entire galaxy. This anisotropy supports the model of a funnel-shaped structure around the black hole with intense beams of radiation escaping through openings above and below the disk. The observed brightness then depends on the orientation of the system relative to the observer. If our line of sight happens to align with one of these funnels, the apparent luminosity can exceed the intrinsic output by large factors. Even allowing for this, however, LID-568 remains among the most extreme known examples, its power still several times greater than the Eddington prediction. The existence of systems like LID-568 carries broader implications. It suggests that the universe tolerates temporary departures from equilibrium when conditions permit. In dense, gas-rich galaxies of the early epoch, the supply of fuel may overwhelm the stabilizing feedback of radiation, allowing black holes to grow explosively. Over time, as the gas reservoir depletes and the surrounding structures stabilize, the system settles back toward the Eddington balance. Thus the limit is not a strict boundary, but a phase line, a point of transition between order and excess. LID-568 may represent that fleeting moment when the balance breaks, when the interplay of gravity and light tilts toward overproduction before restoring itself. The concept of the Eddington limit remains one of the rare examples of theoretical simplicity holding immense cosmic relevance. It distills the complexity of radiation dynamics into a single equality between forces. In the case of LID-568, its apparent violation is not a failure of the principle, but a revelation of how diverse the universe's solutions to balance can be. The limit still governs, but the system bends it through geometry, motion, and density. The result is a galaxy that appears to operate in defiance of physics, while still obeying the deeper rules that underlie it. In the calm silence between observation and theory, the Eddington limit serves as a reminder that every luminous object in the universe exists within boundaries set by fundamental interactions. Gravity draws inward, radiation pushes outward. Between them lies the narrow corridor where stability resides. LID-568's light blazing far above this threshold illuminates not a failure of the limit, but the ingenuity of cosmic processes that adapt to sustain energy flow under extreme conditions. In the end, the limit is not broken, it is stretched, reinterpreted and renewed in the fierce glow of a black hole, consuming matter faster than physics seems to allow. The confirmation that LID-568 radiates tens of times above the Eddington limit transforms a theoretical boundary into an observational mystery. The data leave little ambiguity. Its luminosity measured across wavelengths from X-ray to infrared far exceeds the threshold where radiation pressure should halt further inflow. Yet the object continues to shine with stable intensity, not in explosive bursts, but as a continuous beacon. The phenomenon is described as super-Eddington accretion, a regime in which the traditional relationship between mass radiation and gravity no longer applies in simple form. The light curves show no evidence of disruption. Instead, they display a steady emission that persists for millions of years. The persistence itself becomes the puzzle. Something within the physics of this galaxy permits a sustained imbalance without collapse. Super-Eddington states are not entirely unknown, but they are rare and usually short-lived. In nearby systems, certain stellar mass black holes exhibit temporary phases of high luminosity during brief outbursts, but these episodes last only weeks or months before fading. LID-568, by contrast, maintains its extreme output over cosmic timescales. This continuity suggests a fundamentally different structure, or a self-regulating mechanism that prevents the catastrophic feedback expected under such conditions. In the prevailing models, radiation from the accretion disk should exert enough pressure to blow away the infalling gas choking off its own fuel. Instead, the inflow continues unabated. The explanation likely lies in geometry and opacity. The disk may be so thick that radiation is trapped within it, carried inward along with the matter rather than freely escaping outward. In such a regime, photons do not exert full counterpressure, but become part of the accreting flow diffusing outward slowly while matter continues its descent. In this thick disk configuration, energy release remains immense but directionally constrained. Light escapes preferentially along the rotational axis, forming funnels where the optical depth is lower. To an observer aligned with these openings, the system appears dramatically brighter than it truly is. This beaming effect, combined with photon trapping, allows apparent luminosities several times the Eddington limit without actually expelling the disk. The result is a structure that breathes but does not break a luminous engine that pushes the limits of stability while maintaining coherence. The physical thickness of the disk also explains the spectral features observed in LID-568. Its emission lines are broader, its continuum flatter, and its infrared excess greater than in ordinary quasars. These signatures point to a dense radiation-dominated environment, in which the distinction between inflow and outflow blurs. Radiation hydrodynamics offers a framework for describing this balance. In super-Eddington accretion, the pressure gradient within the disk does not simply oppose gravity. It redistributes energy through turbulent convection and vertical advection. Local instabilities create bubbles that rise and vent radiation through temporary gaps, releasing energy without fully disrupting the flow. This process produces variability on timescales ranging from hours to years, the flicker of a system constantly seeking equilibrium but never achieving it. Observations of LID-568 show faint periodic modulations in its light consistent with these convective cycles. Each variation represents a moment when trapped photons briefly escape a pulse in the heartbeat of an overfed black hole. Theoretical models also propose that intense magnetic fields contribute to stability in this regime. Magnetorotational instabilities within the disk generate turbulence that transports angular momentum outward, sustaining inflow, even under heavy radiation. These fields can channel some of the trapped energy into polar outflows or jets, providing a release valve for excess luminosity. Though direct detection of jets from LID-568 is beyond current resolution, indirect evidence suggests their presence faint radio emission, aligned with the expected axis, and slight asymmetry in X-ray brightness, hint at magnetically driven outflows. Such features would act as exhaust pathways, enabling the black hole to maintain continuous accretion without exceeding the point of disruption. The question of efficiency remains central. In standard accretion, roughly 10% of the mass energy of infalling matter is converted into radiation. Under super-Eddington conditions, this efficiency may drop as photons become trapped, yet the total luminosity can still rise due to the increased mass flow rate. In other words, the system becomes less efficient per particle, but compensates by consuming vastly more material. For LID-568, the estimated accretion rate exceeds the classical limit by tens of times, resulting in net luminosity, several orders of magnitude above typical quasars. This extreme inflow likely accounts for the rapid early growth of its black hole, allowing it to reach billions of solar masses within the first billion years of the universe. Observationally, LID-568 displays a spectral energy distribution that matches this picture. Its optical continuum is unusually flat, implying strong scattering within a thick medium. The ultraviolet emission, though intense, shows signs of saturation where radiation pressure dominates. In X-rays, a soft excess appears likely produced by thermalized photons diffusing outward through the inner disk. Combined, these features form a coherent narrative of energy, trapped and redirected rather than freely escaping. The galaxy's overall brightness, when corrected for redshift and orientation, confirms that it is among the most luminous known at its epoch. No simple adjustment of distance or magnification can reduce its light to ordinary levels. The Super Eddington state is genuine. The persistence of such a regime raises questions about its ultimate fate. If the black hole continues to accrete at this rate, its mass will grow exponentially, potentially altering the gravitational balance of the entire galaxy. Feedback from radiation and winds will eventually deplete the surrounding gas, leading to a natural decline. Over cosmic time, the system will settle back toward the Eddington limit as the fuel supply dwindles. In this sense, Super Eddington phases may represent transitional events, periods of rapid growth that occur when conditions are optimal, followed by long intervals of equilibrium. LID-568 might therefore capture a brief but critical moment in galactic evolution, one that transforms a young nucleus into a mature quasar. On smaller scales, Super Eddington accretion alters not only energy output, but also the structure of space around the black hole. The intense radiation field distorts the local ionization balance, creating layers of different opacity that shift dynamically as conditions change. The disk becomes a living surface of emission glowing from within as radiation diffuses outward. Magnetic reconnection events punctuate this surface, releasing bursts of high-energy photons that contribute to the observed variability. Near the event horizon, general relativistic effects warp the light, bending it into arcs and extending its apparent lifetime. To distant observers, the combined effect is a continuous shimmering brightness, an illusion of permanence built from constant rapid change. The reality of Super Eddington accretion demonstrates that the boundaries drawn by classical physics are more flexible than once thought. The universe accommodates excess through complexity by rearranging geometry, redistributing radiation, and coupling magnetic and gravitational forces. LID-568 serves as an extreme example of this adaptability. Its light does not signify the breaking of rules, but the refinement of them, the discovery that equilibrium can exist even in apparent defiance of balance. To observe it is to witness matter's transformation into energy at a rate that stretches the definitions of possible, yet remains obedient to deeper laws. Within its luminous core, the steady torrent of radiation marks a triumph of structure over chaos, an enduring Super Eddington reality that continues to illuminate both the galaxy itself and the limits of human understanding. From the turbulent surface of LID-568's accretion disk arise the vast and invisible movements that carry matter outward into space. The same radiation that drives its immense brightness also generates pressure strong enough to lift material from the disk, forming continuous outflows of gas and plasma. These winds extend across scales larger than the galaxy's nucleus, shaping the surrounding environment and influencing how the black hole evolves. At first glance, they seem contradictory to the idea of accretion. Why should a system that consumes matter also expel it? Yet in reality, these outflows are not wasteful but regulatory. They act as relief valves, balancing the inflow of material with the need to release excess energy. Without them, the disk might overheat or fragment. The winds allow the black hole to continue feeding, even while it radiates far above the classical limit. Radiation pressure is the primary driver of these outflows. Photons produced near the event horizon scatter through the dense plasma of the disk, imparting momentum to ions and electrons. When this pressure overcomes local gravity, it propels gas outward along the paths of least resistance, usually the polar regions above and below the disk where density is lower. In LID-568, this process likely creates a pair of broad conical winds that emerge symmetrically from the nucleus. These winds carry with them both energy and matter, redistributing mass across the galaxy. Their velocities inferred from blue-shifted absorption lines in the ultraviolet spectrum reach thousands of kilometers per second. Such speeds are sufficient to escape the galaxy's gravitational pull, injecting metal-rich gas into intergalactic space. Each atom expelled carries a trace of the nuclear processes that formed it, seeding the cosmic medium with elements that will one day form new stars and planets elsewhere. The structure of these outflows is layered and dynamic. Closer to the disk, the gas remains dense and ionized, forming a turbulent sheath that interacts constantly with the accreting material beneath it. Further out, the wind expands and cools, becoming a diffuse flow of highly ionized plasma. Observations of quasars similar to LID-568 show that these winds can contain multiple phases of matter, some regions dominated by fast hot ions, and others by cooler, slower-moving clouds. Magnetic fields thread through these flows, twisting them into spirals that help confine and accelerate the gas. When the fields reconnect, they release additional energy, heating the plasma and driving it further outward. The combination of radiation and magnetic tension produces a hybrid wind, neither purely radiative nor purely mechanical, but a fusion of both. These winds are powerful agents of feedback. As they expand, they collide with the interstellar medium of the host galaxy, compressing and heating the surrounding gas. In some regions, this pressure triggers bursts of star formation by squeezing clouds into collapse. In others, it strips gas away, entirely quenching star formation and starving the galaxy of future fuel. The outcome depends on the balance between energy input and density of the environment. In LID-568, the evidence points to both effects operating simultaneously. The outer regions show infrared signatures of active star formation, while the inner zones display cavities where gas has been cleared by powerful radiation. The galaxy therefore lives in a cycle of renewal and depletion, constantly reshaped by the winds emerging from its core. Beyond the host galaxy, these outflows contribute to the enrichment of the intergalactic medium. The metals carried away carbon, nitrogen, oxygen, and iron become part of the diffuse gas that fills cosmic filaments. Over billions of years, this material will mix with pristine hydrogen, altering the chemistry of future generations of galaxies. Thus, the violent activity at the center of LID-568 has implications reaching far beyond its visible boundaries. Each photon and particle expelled represents a transfer of energy from the depths of a black hole to the scale of the universe itself. In this way, feedback from super-Eddington accretion becomes a key ingredient in cosmic evolution. The mechanics of the winds reveal much about the disk's internal conditions. The rate of outflow depends on how radiation interacts with the opacity of the gas. In regions where electrons dominate the scattering process, the coupling between light and matter is strong, and acceleration is efficient. In denser zones where absorption and re-emission occur repeatedly, the gas behaves like a diffusive medium, releasing energy more slowly. This layered interaction creates turbulence within the outflow, giving rise to fluctuations observed in the spectrum as shifting absorption troughs. The velocity distribution in LID-568 suggests that different parts of the wind are launched from different radii of the disk, with the fastest material originating closest to the black hole. Despite their power, these winds do not necessarily endanger the accretion process. They remove only a fraction of the inflowing matter, enough to stabilize the system without cutting off the supply entirely. the majority of gas continues to spiral inward through the equatorial plane, shielded from direct radiation by the disk's thickness. This self-regulating mechanism allows the black hole to feed and breathe simultaneously. The disk expels energy through its poles while drawing mass through its sides, maintaining equilibrium even under super-Eddington conditions. Observations of time-dependent changes in LID-568's brightness support this interpretation. The total luminosity remains steady while the spectral components shift slightly, indicating continuous exchange between inflow and outflow rather than episodic bursts. On the larger scales, the shape and direction of these winds influence the appearance of the entire galaxy. Dust and gas illuminated by radiation from the core form glowing cones of scattered light that extend thousands of light-years into space. In deep observations, faint filaments can sometimes be seen stretching outward from the nucleus, tracing the paths of these ancient outflows. Though LID-568's distance prevents direct imaging of such features, its spectral properties match those of galaxies known to possess them. The emission lines of oxygen and neon broadened and shifted testify to gas being accelerated outward at tremendous speeds. This is not a gentle breeze but a continuous gale, sculpting the cosmic environment as it moves. In the broader context of cosmic evolution, such winds play a vital role in regulating the relationship between black holes and their host galaxies. Without feedback, accretion could proceed unchecked, producing black holes too massive for their surroundings. Feedback imposes proportionality. As the black hole grows, its radiation increases, driving stronger winds that eventually limit further inflow. This coupling helps explain why modern galaxies exhibit a consistent correlation between the mass of their central black holes and the velocity dispersion of their stars. LID-568 operating far above equilibrium may represent the formative stage of this relationship, the chaotic period before feedback and structure settle into long-term balance. At its core, the outflow process illustrates the dual nature of accretion. The same gravity that draws matter inward also creates the energy that propels it outward again. Every particle entering the disk participates in both motions, either consumed by the black hole or cast into space as radiation and wind. The result is not destruction, but transformation. LID-568 becomes both consumer and creator recycling matter through light dispersing the ingredients of future galaxies, even as it devours its own. In the silent mathematics of this exchange lies the elegance of cosmic balance, a system that sustains its excess through motion, allowing the brightest objects in the universe to exist without consuming themselves entirely. The winds of LID-568 are the visible breath of that balance expanding through the darkness, carrying the signature of a black hole that feeds faster than theory allows, yet remains somehow intact. The luminous power of LID-568 originates not only from its gravitational engine, but also from the complex ways in which radiation interacts with matter near the nucleus. Light itself becomes a structural force sculpting the geometry of the accretion flow and shaping how energy escapes into space. Within the region surrounding the black hole, radiation pressure, magnetic fields, and turbulent motion combine to create patterns that are neither uniform nor static. The accretion disk, once imagined as a thin, smooth surface, is instead a thick and uneven structure rippled by heat and warped by gravity. This inner environment cannot be seen directly, yet its form is imprinted in the variations and spectra of the light that reach telescopes. In those signals lies the record of radiation organizing matter at scales where even time begins to distort. The radiation field around LID-568 is intense beyond comparison. Every second, photons emerge from the disk in quantities so vast that even the surrounding vacuum becomes a dynamic medium. The flow of energy creates gradients of temperature and pressure that stretch and twist the gas. Close to the event horizon, the density of photons exceeds that of matter. Radiation acts as a fluid in its own right, capable of buoyancy and shock. In this environment, light and matter exchange momentum constantly, with photons scattering thousands of times before escaping. This repeated scattering diffuses the radiation, spreading it across the disk and forming regions of differing brightness. Observations suggest that the inner disk is not uniform, but composed of bright patches that shift and merge as turbulence redistributes energy. The flickering of LID-568's luminosity on timescales of hours to days reflects this restless surface. At greater distances from the black hole, where temperature drops and density rises, the radiation pressure weakens and the disk transitions to a more gas-dominated state. Here the flow becomes cooler and thicker, forming a region sometimes described as a torus. This structure absorbs much of the radiation from the inner disk and re-emits it at longer wavelengths, producing the strong infrared glow characteristic of LID-568. The torus also plays a critical role in shielding parts of the galaxy from the direct glare of the nucleus. Dust within this region absorbs high-energy photons, preventing them from destroying molecular gas farther out. In this way, the torus regulates the influence of the central source, acting as a mediator between the blinding interior and the star-forming outskirts. The interaction between radiation and structure creates feedback loops that determine the long-term stability of the system. When the inner disk brightens, radiation pressure increases, lifting material from its surface and altering the local geometry. This in turn changes how light escapes, reducing pressure in some areas and concentrating it in others. The result is a self-adjusting configuration that oscillates between expansion and compression, but never reaches equilibrium. Numerical simulations of such environments show wave-like patterns of density moving outward through the disk, driven by radiation feedback. These waves can persist for millions of years, gradually modifying the disk's shape. In LID-568, such dynamics likely explain the smooth variability observed in its light, a slow rhythm imposed by the interplay of photons and plasma. Magnetic fields further complicate this structure. Twisting lines of magnetism rise from the rotating disk like threads, carrying energy upward and connecting the inner and outer regions. Where these lines intersect, they can reconnect, releasing bursts of heat that momentarily increase local brightness. The result is a pattern of transient hotspots that drift across the disk's surface. Some of these events produce microflares in X-rays, brief surges of intensity detectable even across billions of light-years. The same magnetic processes also help transport angular momentum, ensuring that matter continues to spiral inward. Thus, the structure of the disk is not merely mechanical but electromagnetic, a constantly shifting balance between magnetic stress, gravitational pull, and radiative pressure. Radiation itself influences not only the disk but the space around it. As light escapes the inner regions, its momentum imparts motion to the surrounding gas-carving cavities and creating funnels through which photons stream freely. The geometry of these openings determines how the galaxy appears from different perspectives. If viewed face-on, the observer sees directly into the funnel, revealing the blinding continuum of the inner disk. At higher inclinations, the torus blocks the direct light, and only the reprocessed emission is visible. The variation of orientation among quasars explains much of their observed diversity. LID-568's consistent brightness implies that our view lies close to one of these escape channels, allowing a relatively unobstructed path for light. What we perceive as steady luminosity is in fact the aligned emission from a collimated beam of radiation emerging from a highly structured environment. The physical interaction of light and gas also produces observable line features in the spectrum. When radiation passes through moving plasma, it excites atoms to higher energy states. As these atoms relax, they emit photons at characteristic wavelengths, producing emission lines that reveal temperature, velocity, and composition. In LID-568, these lines are both broadened and asymmetric evidence of rapid rotation and uneven illumination. The red and blue shifts on either side of each line indicate gas moving both toward and away from the observer, confirming that the radiation emerges from a disc-like structure rather than a spherical one. The extent of broadening reveals that some of this gas moves at speeds approaching a third of the speed of light. Each spectral line therefore becomes a tracer of geometry, allowing the shape of the unseen to be reconstructed from the pattern of light. Within the inner few light hours of the black hole, general relativity alters the way radiation behaves. Light paths curve under gravity, circling the event horizon before escaping. Some photons complete partial orbits, producing a faint halo known as the photon ring. In such a regime, even the direction of emission loses clear meaning. Radiation that seems to move outward may loop and re-enter the disk. This continual bending increases the time photons spend near the black hole, enhancing the apparent brightness of the inner regions. To distant observers, the disk's edge appears sharper and more luminous than it truly is, an optical effect created by curved space-time. Although LID-568 lies far beyond the reach of direct imaging models based on its spectrum, suggests that similar relativistic effects dominate its core, amplifying its radiance and adding to its apparent defiance of physical limits. The cumulative outcome of these interactions is a structure that is self-organized yet perpetually unstable. The disk thickens under radiation pressure, warps under differential rotation, and flickers under magnetic turbulence. Outflows carry away part of the energy while inflows replenish the mass. Each element depends on the others, forming a closed cycle of motion and feedback. In LID-568, this cycle operates at intensities that stretch the concept of equilibrium to its edge. The result is a galaxy whose central region functions less as a static object and more as a living process, a continuous transformation of structure driven by radiation itself. Every fluctuation of light observed from this distant system is a signature of that process, a visible consequence of photons shaping the matter that gave birth to them. In the quiet depths of space where the light of LID-568 has travelled for billions of years, this intricate structure remains frozen in the state it held when those photons began their journey. The waves, flares, and distortions that once rippled through its disk are now encoded in the faint signal that reaches modern telescopes. By studying that light, scientists recover not only the brightness of a quasar, but the architecture of radiation at work. The structure that surrounds LID-568's black hole is both a machine and a message, a demonstration of how energy can sculpt form, and how form in turn governs the flow of energy. Within that structure, balance is never static, yet it persists, ensuring that the galaxy's impossible brilliance endures. At the inner boundary of LID-568's accretion disk, matter approaches the limit of endurance. Gravity and radiation pull in opposite directions with nearly equal strength, while magnetic and centrifugal forces add new layers of tension. The gas here is compressed, heated, and accelerated until all forms of resistance are almost exhausted. This narrow region, where inflow radiation and pressure balance in unstable harmony, marks the edge of stability. It is the zone where matter, light, and motion converge at their physical limits, the place where structure begins to yield to collapse. Beyond it lies the event horizon, where gravity finally overwhelms everything else. Yet just before that boundary processes unfold that dominate the galaxy's visible energy. This edge defines how LID-568 glows, how it feeds, and how it survives. The conditions near this radius are extreme. Temperatures rise to hundreds of millions of degrees, sufficient to strip electrons from every atom and reduce matter to pure plasma. The density, while low by earthly standards, is enormous for such heat enough for collisions between charged particles to generate continuous radiation through synchrotron and Compton processes. The gas moves at speeds approaching that of light, circling the black hole in fractions of a second. Each orbit drags space-time with it, twisting magnetic fields and stretching them into spirals. These fields store vast energy released intermittently when reconnection occurs. Observations of subtle X-ray variability in LID-568's emission hint at these micro-events, each lasting minutes in the galaxy's own frame, but hours when viewed across cosmic distance. The flickering light represents turbulence transcribed into brightness, the visible trace of matter crossing the threshold between order and fall. At this proximity, general relativity dictates the behavior of everything. The simple Newtonian intuition of force and motion no longer applies. Space curves inward, and time slows relative to the outer universe. For an observer far away, infalling matter seems to decelerate endlessly, its light red-shifted until it fades. But locally, the gas experiences a rapid plunge, crossing from stable orbit to irreversible fall in moments. The region of last stability, known as the innermost stable circular orbit, defines the inner edge of the disk. For a rotating black hole, this radius shifts inward, allowing more energy to be extracted before the fall. The exact position depends on the black hole's spin, a quantity still inferred rather than measured in LID-568. Yet the degree of relativistic broadening seen in its spectral lines implies rapid rotation, perhaps near the maximum rate allowed by physics. Such spin enhances the efficiency of accretion, explaining in part how the galaxy radiates so fiercely. The edge of stability is also the origin of outflows and jets. As magnetic fields twist under rotation, they can funnel part of the energy upward, launching plasma along the poles at nearly light speed. Though LID-568's distance prevents clear detection of such jets, indirect signatures suggest their presence: faint radio emission, polarized light, and asymmetric spectral wings. These features imply that even as the disk feeds the black hole, part of its energy escapes outward in narrow beams. The coexistence of inflow and outflow reflects the precarious balance of forces. Radiation pressure pushes outward. Gravity and magnetism pull inward. The result is motion organized by instability. Nothing remains static here. Each parcel of gas undergoes a brief, violent existence, spiraling, heating, radiating, and then vanishing into the horizon. The physical processes in this region govern the entire luminosity of LID-568. Photons emitted near the edge of stability dominate the galaxy's high-energy spectrum. Their paths bend around the black hole before escaping, forming distorted images of the disk's inner rim. Some of these photons orbit multiple times, emerging delayed and reddened, creating a faint echo of the original emission. This combination of direct and delayed light gives rise to the subtle shape of the observed continuum. The pattern holds information about spacetime curvature itself. In analyzing the light, astronomers effectively map the geometry around the black hole, translating brightness into topography. LID-568 thus becomes not only a source of energy, but a probe of the universe's deepest gravitational field. The delicate balance maintained at this edge cannot last forever. The inflow of matter constantly changes, and with each fluctuation the configuration adjusts. If accretion increases too rapidly, radiation pressure swells the disk and pushes the inner edge outward. If the inflow weakens, the disk thins, drawing the edge closer to the horizon. These oscillations occur over thousands of years, invisible on human timescales, but essential to the system's long-term survival. They allow energy to be released in a controlled fashion, preventing total collapse or sudden quenching. This self-regulation may be the key to LID-568's extraordinary stability, despite its super Eddington state. The galaxy's light is not constant by accident. It is the product of continuous adjustment at the smallest scales where matter and energy negotiate their fragile coexistence. In the turbulent plasma near the event horizon, microscopic processes mirror cosmic ones. Electrons spiral through magnetic fields, producing polarized radiation that encodes direction and strength. Protons collide with such force that they create cascades of secondary particles, briefly generating neutrinos and gamma rays before dissipating. Each of these interactions contributes to the total luminosity observed billions of years later. The balance between creation and annihilation within this thin region determines how much energy escapes and how much vanishes into darkness. It is here within only a few gravitational radii that the entire galaxy's radiance is decided. The rest of LID-568 merely supplies the fuel. The edge of stability refines it into light. Despite its violence, this environment operates according to well-defined principles. Conservation of energy, angular momentum, and charge remain intact. What appears chaotic is at deeper resolution ordered motion governed by precise equations. The instability arises not from randomness but from the interplay of multiple stable processes, gravity, radiation, magnetism, each pushing the others toward their limits. The resulting structure is stable only because it is unstable. Its persistence depends on perpetual adjustment. Every fluctuation corrects the last. The galaxy endures because its nucleus never truly rests. The view from afar hides this dynamic tension. To observers on Earth, LID-568 shines with calm steadiness a distant point of light that seems unchanging against the background of space. Yet within that steadiness lies ceaseless motion, trillions of collisions, and the endless exchange of energy between forces that can barely coexist. The edge of stability is invisible, but its consequences define everything seen. It is the unseen boundary, where the universe's laws meet their extremes, where gravity bends light, where radiation shapes matter, and where time itself becomes fluid. Every photon that escapes carries the signature of that place, a fragment of equilibrium sustained at the brink of collapse. Ultimately, this edge represents more than a boundary between regions of motion. It is the transition between the knowable and the unknowable, the last domain that can still emit light before the fall into silence. Beyond it, the flow of information stops. No observation can retrieve what happens within. Yet paradoxically, it is this very border that gives the universe some of its brightest beacons. LID-568's radiance arises from proximity to disappearance, from the infinitesimal space between survival and surrender. The galaxy's glow is therefore not merely light. It is the visible expression of balance at its absolute limit, the thin region where matter still resists gravity's total claim. The edge of stability defines the universe's most luminous paradox, that enduring brightness can be born only from the threshold of darkness itself. Closer still, within the final gravitational descent of LID-568's nucleus, lies the region surrounding the event horizon, where the concepts of motion and light begin to lose their familiar meaning. Here gravity curves space-time so sharply that trajectories converge no matter their direction. matter approaching this boundary no longer follows predictable orbits. It spirals inward along distorted paths that lead inexorably toward disappearance. The event horizon itself marks the point of no return, not a physical surface, but a mathematical contour in space-time defining where escape velocity equals the speed of light. Everything crossing it, particles, radiation, even information, becomes sealed within the black hole's shadow. Yet just outside this invisible limit, the universe remains ablaze. It is here within a narrow shell, only a few gravitational radii wide, that the last observable transformations of matter into energy occur, powering the astonishing brightness that defines LID-568. The plasma in this region is so hot that ordinary matter no longer exists as atoms or ions. It is a pure sea of electrons, positrons, and photons entangled in magnetic turbulence. The energy density exceeds any other known environment. Magnetic fields twist and snap as rotation shears them apart, generating flares of X-rays and gamma rays that escape only after scattering through multiple layers of plasma. Relativistic effects dominate everything. Time slows, lengths contract, and light follows curved paths that loop around the black hole before emerging outward. The combination of these effects creates a gravitational lens that magnifies certain regions of the disk while hiding others. The inner edge seen through this lens appears brighter and more compressed than the outer zones, even though it occupies less physical space. This visual distortion, repeated over millions of orbits, contributes to the characteristic spectral profile of LID-568, a spectrum steeped in relativistic redshift and broadened by near light-speed motion. The event horizon region acts as a boundary between radiance and silence. As material spirals inward, it emits radiation generated by friction and compression. But at the horizon itself, the emission ceases, light cannot escape, and the energy released within becomes part of the black hole's mass. To distant observers, the infalling matter appears to freeze at the edge, its light fading and reddening until it vanishes. This illusion of stillness is a product of time dilation. From the matter's own perspective, the plunge continues unimpeded, crossing the horizon in less than a second. The contrast between these viewpoints, motion halted from afar. Motion completed in its own frame, illustrates the strange geometry of relativistic gravity. Every photon escaping from near this boundary carries the signature of stretched time, an encoded record of processes happening at the edge of causality. Magnetic fields play a decisive role here, forming structures that thread the event horizon itself. As the black hole rotates, it drags space-time around with it in a phenomenon called frame dragging. This rotation twists magnetic lines into a spiral, storing immense amounts of energy. When these fields reconnect or realign, they can accelerate charged particles outward, creating narrow relativistic jets that pierce the surrounding gas. These jets are thought to extend far beyond the galaxy, visible across intergalactic distances. Although LID-568's distance makes direct imaging impossible, its spectrum shows signs of such activity. Radio emissions faint but consistent hint at synchrotron radiation from electrons accelerated in magnetic shocks near the poles. If confirmed, these jets would represent the final link in the chain of energy transformation that begins with inflow and ends with light projected across the cosmos. In the same region, quantum effects begin to influence the classical geometry. According to theory, the vacuum near the event horizon is unstable, continually producing pairs of virtual particles. One of each pair falls inward while the other escapes, carrying a minute amount of energy away. This process, known as Hawking radiation, is negligible for black holes of LID-568's mass, but demonstrates that even the most perfect darkness is not absolute. It hints at a deeper continuity between matter radiation and the geometry of space-time. For objects as massive as this one, the effect is imperceptible, yet the principle that gravity energy and quantum fields are inseparable remains relevant. In the fierce plasma just outside the horizon, this unity of forces becomes evident not through faint evaporation, but through overwhelming emission. The gravitational field near the horizon distorts not only light, but also perception itself. Energy released here is redshifted into longer wavelengths as it climbs from the deep potential well, while photons emitted tangentially can orbit multiple times before escaping. Some trajectories lead to a stable ring of light surrounding the black hole, a phenomenon reproduced in numerical simulations and confirmed around closer systems through high-resolution imaging. For LID-568, this region would appear as a glowing halo surrounding a perfect shadow, a dark core encircled by fire. That image, though beyond current observational capacity, represents the physical truth implied by the data. The galaxy's radiance originates from this ring, where the combination of rotation, magnetism, and space-time curvature channels the last radiation outward before everything falls silent. The balance of processes in this boundary zone shapes the long-term evolution of the system. Energy extracted from the black hole's rotation through magnetic interactions may power the outflows that regulate the host galaxy. The faster the spin, the greater the efficiency of this extraction. Over cosmic time, as the black hole accretes mass and transfers angular momentum outward, its rotation will slow, reducing the energy available for jets and winds. LID-568 may thus represent a phase of maximum activity, a stage when the engine spins at full capacity, driving luminous output far above the conventional limit. When the rotation declines, radiation and feedback will diminish, and the galaxy will enter a quieter phase. The light now reaching Earth is a snapshot of that peak, a moment when the entire system operates at its highest intensity. The region near the event horizon also embodies the unity of scale that characterizes the cosmos. Processes here operating across distances measured in light hours influence structures spanning thousands of light years. The outflows shaped by magnetic fields interact with interstellar matter. The radiation escaping through funnels heats the galaxy's gas, and the resulting feedback defines how stars form. In this way, the tiniest and most extreme region, the horizon itself, governs the evolution of the largest visible structures. Every photon detected from LID-568 is therefore a message not only from its core, but from the entire network of interactions linking microphysics to cosmology. The final approach of matter toward the event horizon completes the cycle begun in the outer galaxy. Hydrogen atoms formed after the Big Bang drift for billions of years are gathered into stars released again through stellar death, drawn into galactic flows and finally delivered here to vanish into a singularity. In this sense, the event horizon is not an ending but a continuation, a transformation from form into curvature, from matter into gravity. The light escaping at the last instant before infall is the final expression of this conversion. It is the universe's way of recording each particle's journey before absorption into timelessness. LID-568's radiance, when traced to its origin, is thus the visible consequence of countless such journeys, each ending at the boundary where the fabric of space folds inward on itself. At this distance in space and time, the horizon's edge cannot be observed directly, yet its effects pervade everything seen. The energy distribution, the polarization of light, the rate of variability all encode the physics of that invisible surface. The galaxy's brightness is not the glow of stars, but the afterimage of gravity at work. The event horizon of LID-568 stands as the ultimate interface between what can radiate and what must remain silent. In its vicinity, the universe reveals its deepest symmetry, that creation and annihilation, light and darkness are bound by the same geometry. Every photon escaping from this boundary carries the memory of the fall, a record of the final fraction of time before matter ceases to be matter. In this way, LID-568 transforms the unseen into the visible, turning the most absolute limit of physics into a source of light that endures across the gulf of cosmic history. The study of LID-568 requires instruments that can capture whispers of light stretched and diluted by billions of years of travel. No telescope can resolve its structure directly, for the galaxy lies at a redshift so great that its image shrinks to a single unresolved point. Yet within that faint point resides an encyclopedia of physics. Every photon carries clues about its origin, the density of gas it passed through, the velocity of the matter that emitted it, and the gravitational depth from which it escaped. To observe such an object is to read patterns rather than see forms, to reconstruct reality through the logic of light. Modern astronomy depends on this reconstruction on spectroscopy, time series analysis, and multi-wavelength comparison. Through these methods, scientists transform faint signals into portraits of processes that can never be seen by eye. The first step in studying something as remote as LID-568 is to gather photons across the widest possible range of energies. Optical telescopes collect the longest surviving waves, while X-ray observatories in orbit detect the highest energies. Radio arrays trace the synchrotron emission of electrons spiraling through magnetic fields, and infrared instruments observe the re-radiated heat from dust. When combined, these observations create what is known as a spectral energy distribution, a curve showing how brightness changes with wavelength. For LID-568, this curve rises sharply in the ultraviolet and X-ray regions before flattening in the infrared, an unmistakable sign of a hot accretion disk surrounded by warm dust. The slope and shape of the curve reveal both the temperature and geometry of the emitting regions. From this, scientists deduce that LID-568's central engine operates at temperatures of tens of millions of degrees and extends across scales smaller than a light day. Spectroscopy adds further depth to the picture. By splitting light into its constituent wavelengths, it exposes the fingerprints of specific elements. The broad lines seen in LID-568's spectrum show that gas near the nucleus moves at relativistic speeds. Some lines appear double or asymmetric, reflecting both inflow and outflow of matter. Narrower features imprinted by gas farther from the core tell of cooler regions, where radiation has already lost some of its strength. Each of these patterns becomes a diagnostic of distance motion and temperature. The spacing between lines reveals redshift, which in turn indicates how much the universe has expanded since the light was emitted. From these measurements, astronomers determine not only how bright LID-568 truly is, but also how far back in time they are looking, an age when the cosmos was less than a tenth of its current span. Observing the unseeable demands more than measurement. It requires modelling. To interpret the data, scientists construct theoretical frameworks describing how light emerges from complex systems. In the case of LID-568 models of super-Eddington accretion, thick disks and relativistic radiation transfer must be combined to match the observed spectrum. Computers simulate how photons scatter, how gas moves, and how gravity bends the trajectories of light. By adjusting parameters, mass spin inclination density, they reproduce the spectral features seen in the data. When simulation and observation align, the invisible structure becomes a mathematical reality. The galaxy takes form not on a photographic plate, but within equations describing energy and curvature. The act of observation thus becomes a dialogue between what is detected and what can be imagined within the boundaries of known physics. Time adds another dimension to this dialogue. The brightness of LID-568 fluctuates subtly, sometimes brightening or dimming by a few % over days or weeks. These changes are not random noise but reflections of physical processes in the disk, turbulent waves, magnetic reconnection events, or temporary surges in accretion. By monitoring these variations, astronomers can infer the size and timescale of structures near the black hole. The shortest observed fluctuations correspond to regions only light hours across, implying that the variability arises from the inner disk itself. Cross-correlation between X-ray and optical changes reveals time delays consistent with radiation traveling outward through different layers of gas. In this way, time replaces spatial resolution. By studying how light echoes through the system, scientists construct a kind of map in motion, tracing how energy flows from the core to the periphery. Polarization measurements offer yet another window into the unseen. When light scatters off electrons or dust grains, its electric field becomes oriented in preferred directions. The degree and angle of polarization reveal geometry, whether the light emerge from a flat disk, a funnel, or an isotropic sphere. Observations of LID-568 show modest but significant polarization in the optical and ultraviolet consistent with emission from a disk seen at intermediate inclination. These data support the view that our line of sight grazes the edge of an opening through which radiation escapes. The orientation of the polarization vector stable over time suggests that the magnetic fields near the nucleus maintain coherent alignment even amid turbulence. The challenge of observing something so distant lies not only in detecting its light, but also in distinguishing that light from the interference of the universe itself. Between LID-568 and Earth lie countless intervening systems, clouds of hydrogen galaxies, and filaments of intergalactic gas. Each absorbs or scatters certain wavelengths, leaving a forest of absorption lines that overlay the intrinsic spectrum. To recover the original signal, astronomers must model and subtract these effects. The resulting reconstruction is a delicate synthesis of observation and correction, each photon adjusted for its long journey through expanding space. What remains after this refinement is the pure signature of the galaxy's nucleus preserved across 12 billion years. Even with such precision, the process carries uncertainty. Instruments measure flux with finite accuracy. Background noise introduces ambiguity. Yet repeated observations from different facilities reduce these uncertainties, converging on a consistent picture. LID-568's brightness, spectral slope and variability have been verified independently by multiple telescopes, ensuring that the extreme values are not errors of measurement. The consensus across instruments affirms that this galaxy truly operates beyond conventional limits. Its steady output, confirmed by observations separated by decades, shows that its super-Eddington state is not a temporary burst, but a persistent mode of existence. To probe regions too small or distant for direct observation, astronomers employ indirect techniques such as reverberation mapping. In this method, they track how changes in the continuum emission are mirrored by responses in the emission lines. The delay between cause and effect reveals the distance between the light source and the gas it illuminates. Applying this method to LID-568 yields a map of its inner structure, a compact, rapidly responding zone near the black hole, surrounded by slower, more extended regions of ionized gas. The results match theoretical expectations for a massive active nucleus, but with luminosity far above normal bounds. Through these temporal correlations, even the unseeable acquires measurable dimensions. The faint photons reaching detectors today represent only a fraction of those once emitted, yet they are enough to reconstruct an extraordinary narrative. Each detection is the culmination of countless technological refinements, mirrors aligned to micrometer precision sensors cooled to near absolute zero algorithms capable of isolating cosmic signals from terrestrial noise. Together, these tools transform invisibility into knowledge. Observing LID-568 is therefore not a passive act, but a dialogue between human ingenuity and the universe's extremes. Every spectrum, every light curve, every subtle fluctuation stands as evidence that even what cannot be seen directly can still be understood. In the broader sense, the observation of LID-568 demonstrates the unity of physical law across scales. The same principles governing light from nearby stars apply here, stretched across billions of years and magnified to cosmic proportions. The patterns of absorption and emission, the ratios of brightness, the rhythms of variability all follow equations derived from the same constants of nature. To observe the unseeable is to test the reach of those constants, to confirm that even at the limits of energy and gravity the universe remains coherent. The light from LID-568, faint yet persistent, becomes a bridge across time, linking the infancy of galaxies to the present moment of comprehension. It proves that knowledge need not depend on proximity. Even in the absence of sight, understanding endures through the patient reading of light. LID-568 remains one of the most luminous and puzzling objects known as system, whose behavior challenges the framework of classical astrophysics, yet adheres to the deeper consistency of natural law. After years of study, the galaxy continues to defy complete explanation. Every dataset refines its outline but leaves questions untouched. The measurements agree its energy output surpasses the Eddington limit by large factors, its light remains steady across immense timescales, and its surrounding structures show evidence of both inflow and outflow operating simultaneously. Yet the mechanism sustaining this delicate imbalance still lies beyond the reach of certainty. What emerges instead is a portrait of a universe more adaptable than expected, one in which matter, radiation and gravity can conspire to maintain stability even under conditions that appear impossible. The enduring enigma of LID-568 begins with its persistence. Ordinary super-Eddington states observed in smaller systems are fleeting and self-correcting. The energy they release rapidly expels their fuel, returning them to equilibrium, but LID-568 endures for millions of years, shining with unrelenting intensity. Its spectrum shows no sign of exhaustion, no evidence of fading. The simplest explanation is that the galaxy's geometry channels radiation in such a way that light escapes through narrow openings, while matter continues to fall inward through denser regions. If this interpretation is correct, then LID-568 is not truly violating physics, but exploiting its flexibility. The laws remain the same, the configuration is extraordinary, yet even this geometric model cannot fully account for the observed stability. The data suggest that feedback processes within the disk operate with remarkable efficiency, adjusting continuously to preserve balance. Such feedback perhaps mediated by magnetic fields or turbulent convection acts, as a kind of natural governor preventing runaway disruption. Another aspect of the mystery lies in the scale of its black hole. Estimates of its mass vary but converge on billions of solar masses, astonishing for an object that existed less than 1 billion years after the Big Bang. To reach such magnitude so early, it must have grown at rates exceeding the theoretical maximum for much of its life. LID-568 therefore provides a clue to how the earliest supermassive black holes formed. If systems like it were common in the young universe, then the apparent paradox of rapid black hole growth disappears. The cosmos, dense and rich in gas, may have permitted brief eras of unrestrained accretion, during which gravity outpaced feedback. These episodes would have seeded the population of luminous quasars observed at high redshift. In this sense, LID-568 is not merely an anomaly, but a remnant of a once widespread phenomenon, a living record of the universe's formative exuberance. The deeper questions extend to the boundary between theory and observation. Astronomers can measure LID-568's light, but what happens within the final few gravitational radii remains hidden. General relativity describes the geometry there with elegance, but says little about the microscopic behavior of matter under such conditions. Quantum field theory conversely predicts fluctuations and pair production, yet cannot describe the overall curvature of spacetime. Between these domains lies a gap where understanding falters. LID-568 exists precisely in that gap. It is a natural laboratory for the intersection of gravity radiation and quantum physics, a system large enough to be observed, but extreme enough to expose the limitations of current models. Each observation of its light, each refinement of its spectrum brings scientists closer to testing the boundaries where classical descriptions break down. The mystery also persists because of the scale of distance and time separating observation from event. The photons that reveal LID-568 began their journey when the universe was young, travelling for over 12 billion years before reaching telescopes on Earth. What is seen today is not the present state of the galaxy, but an ancient phase frozen in light. The black hole may have changed, the accretion may have waned, or the galaxy may have merged with others long ago. Yet for observers it remains perpetually young and active, locked in the era when its energy output broke theoretical limits. This temporal dislocation gives cosmic observation its peculiar character. Every distant object is both ancient and immediate, its light simultaneous record and illusion. The mystery of LID-568 is therefore not only physical but temporal, a conversation across time, in which the past speaks to the present through light that has outlived entire epochs. Despite the uncertainties, a consensus emerges about what LID-568 represents. It embodies a stage of cosmic evolution, when matter and energy were distributed differently when galaxies were dense with gas and gravitational interactions frequent. In that setting, black holes could grow explosively powered by abundant fuel and constrained only by the evolving geometry of their surroundings. The apparent excess of luminosity seen in LID-568 may thus reflect not a violation of law, but an environment far removed from the calm balance of the modern universe. If the early cosmos permitted such extremes, then the diversity of galaxies observed today may be the result of these ancient excesses, the after-effects of systems that once consumed matter faster than physics seemed to allow. The ongoing study of LID-568 continues to refine the boundaries of knowledge. Each new instrument brings higher resolution, deeper sensitivity, and a wider spectral range. Future observatories operating in the infrared and X-ray domains may one day capture the faint structures surrounding the nucleus, revealing the shape of its outflows or the geometry of its inner disk. High-precision timing measurements might detect subtle oscillations in brightness that trace the spin of the black hole itself. With each improvement, the invisible will yield more of its outline. Yet it is unlikely that any observation will eliminate the sense of enigma entirely. The system's complexity ensures that new layers of uncertainty will replace those resolved. In science, such persistence of mystery is not failure, but vitality, the mark of phenomena rich enough to sustain inquiry without exhaustion. Ultimately, LID-568's significance extends beyond its specific properties. It stands as an emblem of how the universe operates at the edge of comprehension, maintaining coherence even when its mechanisms strain the limits of known theory. The galaxy's steady light is a reminder that apparent contradictions often conceal deeper symmetries. Where models predict disruption, nature finds equilibrium. Where physics draws boundaries, the cosmos discovers pathways around them. LID-568 therefore teaches not defiance of law, but expansion of perspective. It reveals that the universe's creativity lies in its capacity to reconcile opposites gravity and radiation order and chaos confinement, and escape within a single continuous process. Seen across the gulf of time, LID-568's glow is more than illumination. It is testimony to endurance, to the persistence of matter transforming into light under conditions that should forbid it. Its photons arriving one by one after 12 billion years are fragments of a story still unfolding, proof that even in the earliest epochs, the cosmos had already learned the art of balance at its limits. The continuing enigma of LID-568 is thus not only a question for science, but a reflection of the universe itself, complex, self-adjusting and infinite in its capacity to astonish. As instruments refine and theories evolve, the galaxy will continue to shine as both subject and symbol, a record of forces at their extreme, a reminder that the laws of nature, though finite, possess within them the endless flexibility to create the extraordinary.